Hey guys, today we're going to do section 2 of chapter 2, tangent lines in the derivative. So we're going to progress towards um, looking from a limit definition of a derivative to a rule of a derivative, but we've got to get there first. So that's what our first um, priority is here today. Lots of highlighting. Make sure you've got your highlighter handy. All right, lesson 2, tangent lines and the derivative. There are two main concepts in calculus known as the tangent line problem, which are your derivatives, and the area problem, which are your integrals. Integrals will be the second half of the year where we kind of undo the derivatives that we've already found. So both of these big ideas are related to limits. In the previous lesson, we applied the difference quotient to a function y equals f of x and found a general slope formula. This calculated the slope of a tangent line at any point on the curve, provided the limit exists at that point. This general slope formula is also a function and is called the derivative function of f of x, or f prime of x. That prime looks like an apostrophe. A function that has a derivative at a point is said to be differentiable at that point. And we're going to get continuity and differentiability together later on. The definition of the derivative of the function f with respect to x is the function f prime, whose value at x is the slope is equal to f prime of x, equals the limit as x approaches 0 of f of x plus h minus f of x over h, provided that the limit exists. Note the domain of f prime, which consists of all values of x in the domain of f of x, for which the limit exists, may be smaller than the domain of f. If f prime of x exists, we say that f is differentiable at x. Proper notation down here at the bottom, I have highlighted the two that we will be using most. F prime of x is actually the most used, and then y prime. dy dx we will use a lot when we do implicit differentiation, which is chapter 7. And df dx, we don't use very often. You will from time to time see this. Just understand that that indicates you are finding the derivative. The limit definition of the derivative. We will be doing a lot of this today. Graphically, the derivative of a function at a point P is the slope of the tangent line to the graph of y equals f of x at P. Derivative equals slope. Numerically, the derivative at a point is the limit of slopes of the secant lines or the limit of the difference quotient. And verbally, a function f is said to be differentiable at a point a, f of a, if and only if it has a defined slope at x equals a. If a function does not have a tangent at a specified point, then the function cannot have a slope there either. Excuse me. All right, so example 1, use the limit process of the derivative to find the general formula dy dx for the derivative of f of x equals 2x squared minus 3x. So we are looking for dy dx. And we're going to use that limit definition of the derivative. So the limit is at h approaches 0, f of x plus h minus f of x over h. So we're going to take our function, 2 times x plus h squared, and I forgot that limit. Y'all don't let me forget that as much as I tell y'all not to forget it. The limit is h approaches 0 of 2 times x plus h squared minus 3 times x plus h minus the function f of x. As always, if you have questions, make sure you mark it with a sticky note or write it in different color. And that's, excuse me, all over h. The limit is h approaches 0. And I'm going to do a little bit of work here to kind of alleviate some space. X plus h squared is going to be x squared plus 2xh plus h squared. FOIL method there. And then those two are just going to be distributing the negatives. So x squared plus 2xh plus h squared minus 3x minus 3h minus 2x squared plus 3x all over h. Remember, our goal is to eliminate that h in the denominator so we can sub in h equals 0. So I forgot my 2 here, so I need to go back in and distribute the 2. I wrote it really small, so I ended up forgetting that when I plug it in. So I'm going to distribute the 2. And see where I can cancel. So my 2x squareds are going to cancel. My 3x's are going to cancel. And I get the limit as h approaches 0 of 4xh plus 2h squared minus 3h over h. Factor out that GCF of h on top, 4x plus 2h minus 3 over h. Cancel those h's. And remember that h is equal to 0. So your derivative dy dx is equal to 4x minus 3. If you would like to try example 2 on your own, we're going to do the same thing. You're welcome to pause the video. This time we're using f prime of x notation. It does not matter. They all mean the same thing. The limit as h approaches 0 of x plus h squared minus x plus h, and then minus your function, x squared minus x, all over h. Very obviously, if you miss your substitution, the rest of your problem is going to be incorrect. So make sure that you are very aware of what you're doing. FOIL method, x squared plus 2xh plus h squared. Distribute your negative and distribute your negative again. All over h. X squareds are going to cancel. X's are going to cancel. And we have the limit as h approaches 0. Go ahead and take that h out. So we have h times 2x plus h minus 1 all over h. Cancel those h's out. Remember that h is equal to 0. So f prime of x is equal to 2x minus 1. It is important, even though the derivative has multiple ways for you to represent it, it is important that you use what they tell you to in the problem. And in this case, they say find f prime of x, so your answer should say f prime of x. In example number 1, it said find dy dx, so your answer should say dy dx. Even though they mean the same thing, make sure that you're using the correct notation. Now we're going to look at another form of the derivative. The numeric value of the derivative at a point x equals a is also found by finding the slope of the tangent line, limit as h approaches 0, f of a plus h minus f of a over h, or f prime of a is the limit as x approaches a of f of x minus f of a over x minus a, provided the limit exists for all a for which the limit exists, f prime of a is a function of a. So we're going to use the alternate form of the derivative to find f prime of a, which a is 1, for f of x equals the square root of 3x plus 1. Pay close attention to what we're doing here. It will really help you out on our last example. So we're going to start by finding f of 1. That's the square root of 3 plus 1, square root of 4 is 2. So what we have just found here is f of a. And you'll notice in both of our alternate forms, f of a is required. Right there and right there. So we've just found f of a, f of 1. Now we're going to start the process of finding f prime of a. the limit as x approaches 1. And we're going to do f of x minus f of a over x minus a. So we're using this particular definition here. Now, we are going to go ahead and looks like we might can do some direct substitution. Let's see. 3 times 1, 3. 3 plus 1 is 2. No, we need to go ahead and rationalize. So square root of 3x plus 1 plus 2 over the square root of 3x plus 1 plus 2. So the limit as x approaches 1 of 3x plus 1 minus 4. I'm sorry, that should be a 1, not a 2. That one should be a 2. I apologize for that. X minus 1 square root of 3x plus 1 plus 2. Make sure you make that correction. That was my fault. As x approaches, or x minus 1. Because the bottom is x minus a, not x minus f of a. So x minus a, which is 1. That is the main reason direct substitution is not going to work, because 1 minus 1 would be 0. All right, so let's clean this up a little bit. The limit as x approaches 1 of 3x minus 3 over x minus 1 square root 3x plus 1 plus 2. All right, recognizing that the top can be factored with a GCF. And then by doing that, we can factor out our x minus 1s. Now we're ready for some direct substitution. So we have 3 on the top. X approaches 1, so we have the square root of 4 plus 2, which is 3 over 4. So f prime of 1 is equal to 3 over 4. When finding the derivative at a point, there are 2 approaches. You can either find the general formula first and substitute your x value, or you can substitute the x value from the start. If you're given 1 point, a f of a, then you are finding the instantaneous rate of change at x equals a, the slope of the tangent line, the derivative at x equals c, or f prime of c equals the limit as h approaches 0 of f of a plus h minus f of a over h. If you're given 2 points, a f of a and b f of b, you're finding the average rate of change on the interval from a to b, the slope of the secant line, or f of b minus f of a over b minus a. Just some added information there for you. Estimating the derivatives of a function at a point. Find the slope of the tangent line to the hyperbola y equals 2 over x at x equals 3. All right, the first thing that you should recognize is that your a value is going to be 3. And a and b are going to go together. So a equals 3 is going to be the same for both a and b. All right, so we're going to find the slope of the tangent line. X equals 3. Here is our function. So the limit as x approaches 3, f of x minus f of a over x minus a. So 2 over x, there's f of x, minus f of a, 2 over 3 over x minus a, which is x minus 3. You will need a common denominator. Don't forget cross, cross, across. So the limit as x approaches 3 of 6 minus 2x over 3x times the reciprocal of the denominator, 1 over x minus 3. Factor. Cancel with a -1. So you have -2 over 3x. You are going to find the slope at x equals 3. So the slope is -2 over 3 times 3, which is -2 over 9. For part B, you're simply using a different definition of the derivative to find the slope of the tangent line to the hyperbola y equals 2 over x at x equals 3. So the limit as h approaches 0, remember a is 3, 2 over 3 plus h minus f of a, 2 over 3 over h. Again, cross, cross, across, you need a common denominator. Six minus 2 times 3 plus h over 3 times 3 plus h times 1 over h. The limit as h approaches 0. Clean it up just a little bit. You get 6 minus 2h over 3h times 3 plus h. Simplify. Limit as h approaches 0. 6 minus 6, 0. So -2h over 3h times 3 plus h. Your h's cancel here, and this h is equal to 0. So you have -2 over 3 times 3, which is -2 over 9. Notice that it doesn't matter which of your two formulas you use. Your slopes are the same. So verbally speaking, you're finding all of the following. The slope of the tangent line to f at x equals a, the instantaneous rate of change of f at x equals a, the derivative of f at x equals a, and the limit of the difference quotient of f at x equals a. For example number 5, you're going to need either colored pencils or colored pens and a ruler. So if you want to pause the video, go grab those, come right back. We're going to do all kinds of things with this graph. You will definitely need a ruler, and then we're going to color code them to fill out our chart. So the graph of the function f of x is at the right, and it is differentiable on the interval from a to a plus h. So we're going to use the expressions in the first column. We're going to state whether the expression represents a length or a slope, and we're going to draw the geometric representation of the expression on the graph using, and this says a blue pencil to represent any length and a red pencil to represent any slope. We're not going to do that. We're going to just do our colored pencils for each one. All right, f of a. So if this is a, then this value represents f of a, this point. This point is definitely not a slope. You can have a slope at a point, but this is just a point. So it is a length. And our terminology is it is the value of f of x at x equals a. In other words, it's your y value. f of a plus h, here's a plus h, here's f of a plus h. Also a length, very similar to number 1. It is the value of f of x at x equals a plus h. So it is your y value when x is a plus h, and this would be your y value here. All right, f of a plus h minus f of a. So this is f of a plus h, and this is f of a. So if we were going to subtract the two, that would be our value. So it's a y value minus a y value. Definitely not a slope. And because slope and length are our only two options, this one is a length. It is the difference in y values for f of x between x equals a plus h and x equals a. And that's what we just talked about. We see the h represented here. It's already drawn in for us, so this will be number 4. Again, not a slope. It is a displacement. It's the distance on the x-axis between x equals a and x equals a plus h. And now we're starting to get into more of what we have been working on today. F of a plus h minus f of a over h, we know is a derivative, and a derivative is a slope. So that is going to be our slope here on our line that is graphed for us. It is going to be our average rate of change of f of x on the interval a to a plus h. We are finding the slope of our secant line. And all of these formulas are in your notes with all of their information. So if you need to look back at those at any time, feel free to do so. Number 6, the limit as h approaches 0, f of a plus h minus f of a over h is also a slope. This is going to be the slope of our tangent line here at A. And it is the instantaneous rate of change of f of x at x equals a. It is a tangent line slope which is your derivative. And f prime of a, represents the same thing. It's just another way to write it. So also a slope. And we're just going to say this is the same as number 6. So we're not going to rewrite that again. And then go back up to our graph and put a number 7 right there beside it. This is graphically what your derivative looks like. Again, pause your video at any point when you need to catch up. All right, understanding the derivative symbolically. Oftentimes you'll be asked to extend your knowledge base for operations where you need to recognize functions, procedures, processes, theorems, and properties. You might also need to decompose or deconstruct mathematical operations symbolically. Here is a sample of such instances. So each of the following expressions represents the derivative of some function y equals f of x for some value x equals c. Your goal is to identify the function and the value of c, a, x, all the same. So we're going to go ahead for each of these and write in what we need to find. And you don't need a whole lot of work for these. So we're just going to go ahead and put in f of x and c. So we're going to think back to those formulas that we have looked at today. And in this particular case, we're going to look specifically at the limit as h approaches 0 of f of a plus h minus f of a over h. And the reason we're going to look at that is because we're looking at our denominator and we see that it matches the denominator that we see here. So if the square root of h plus 4 is supposed to represent f of a plus h, then that means a, which is c, has to be 4. So your function, if this is a plus h, which we plug in when we see an x, then your function would be the square root of x. Because if you were to plug in a plus h here, you would get the square root of 4 plus h, which is the same as h plus 4. So that's an example of a decomposition. Can be a little challenging. Just remember your formulas. We're going to do the same thing here for part B. The limit as h approaches 0, e to the cosine of pi plus h minus e to the first power over h. Again, we're going to use the formula that we wrote out here to the side of part A. Your a value, remember, this is going to be f of a plus h. So your pi value will be your a. So what makes e to the cosine of a pi plus h, what makes it look like f of a plus h? Well, we know that a is your number, so a plus h. So a plus h goes in for x. If a plus h goes in for x, then your function is e to the cosine of x. E to the cosine of a plus h, e to the cosine of pi plus h. If you want to pause and try a little bit of these on your own, you're welcome to do so. Same formula because we're still over h. Tangent of 2 times 2 plus h minus tangent of 4 over h. Notice where we're focusing. We start here to let us know which function to use. And then from there, we look at what is a. Because remember, we're looking at f of a plus h. And then from there, what is our function? So in this case, we have tangent of 2 times 2 plus h. So there's your a value, which is 2. So a plus h would be your x. So your function would be tangent of 2x. Same function here. Limit as h approaches 0, 1 over h, natural log of 6 plus h over 6. Keep in mind f of a plus h. A is going to be your number. So c will be 6. And then your function would just be natural log of x. When you plug it in, your f of a plus h would just be your function ln x. Moving on to E and F, you will notice their denominators are different. They're no longer just h, so we will use our different alternate limit definition as x approaches a of f of x minus f of a over x minus a. I think these are a little bit easier myself. It's very easy for you to identify a. X minus a is your denominator. So x minus 3 is x equals x minus a. So negative 3 is negative a, so a is 3. In other words, it's going to be the opposite of your number that's in the denominator. Denominator is negative 3. Negative 3, opposite of negative 3 is positive 3. So it tells you f of x is the first part of your function, f of x. So x minus 1 squared. Again, I think these are much easier than a through d. They still require you to think a little bit. So if f of x is the first part of our function, then f of x is the cubic root of x minus 6. And if x plus 2 is equal to x minus a, then a is negative 2. So this concludes the notes for section 2. Again, if you have questions, make sure that you ask. One last thing on this last part here, depending on your denominator, depends on which function you use to determine the pieces that you're asked to find. Please let me know if you have any questions. You may email me, or we can get in on a Zoom chat. Have a great afternoon, and I'll talk to you soon.